How's everybody's conference going so far? Good? Yeah? Cool. All right. Yeah, so I like long titles that are almost tongue twisters. So this is the Unbreakable Code who's breaking one World War II. And because it's a workshop, I got to add another word, so I'm very excited. It's building the Unbreakable Code who's breaking one World War II. As Mina said, my name is Aji. I work at a place called Thoughtbot. And today we're going to be working with Enigma. Just kind of a baseline to see where we're all at. Who here has heard of the Enigma machine? Nice, cool, and know about the place Bletchley Park? A little bit, great. So we're all operating with some shared understanding. I'm going to briefly go through the story and kind of the functionality of the Enigma machine. So you may have learned that in the 1930s and 40s, there was a war involving many nations and peoples across the globe. So many, in fact, they called it a world war. It was the second of its kind. The particulars of the conflict are not what we're going to discuss today. If you're interested in the period, I believe there have been a few movies and TV shows, even books, where you can find out more. Just a few. For our purposes today, all that's important is that you know that on opposing sides of the conflict were Germany and the United Kingdom. And at the time, long-distance communication was done in Morse code over radio and could be intercepted by your opponents in much the same way that we intercept radio stations in our cars. The messages needed to be encrypted. So the German solution for encryption was this, the Enigma machine. Not that much bigger than a typewriter, Enigma would encipher a given message before it was sent over the airwaves. The receiver of the message would also have an Enigma. Given the same settings that encoded the transmission, they could reconstruct the original message. The British solution for decrypting was this, Bletchley Park. Housed at this estate in Buckinghamshire was Britain's GC and CS, Government Code and Cipher School. Their work was kept secret until the 1970s, but several thousand men and women, mostly college-aged, were tasked with cracking the German enciphering system. So if you know of Bletchley, the story you've likely heard is his. This is Alan Turing of the Turing test, Turing machines, Turing patterns, the negative proof of the Entscheidungsprobleme. Or maybe you've seen him on the 50-pound note. Building on the work of Polish codebreaker Marian Rejewski and his precursor machine called Bomba, Turing realized that a quirk of the Enigma's wiring could be exploited and designed a special-purpose computational engine that was made real by the engineering brilliance of Harold Keane and the British Tabulating Machine Company. After incorporating a crucial insight by English mathematician Gordon Welshman, Bletchley's secret weapon was christened Bomb. On 108 cacophonous rotating drums, Bomb crunched through 17,576 possible Enigma settings in just 20 minutes. Depending on who you ask, the work at Bletchley shortened the war by 2 to 4 years. And if you're interested in hearing more about what it was like to be a part of Bletchley's operation, I would recommend The Secret Lives of Code Breakers by Sinclair McKay. So the Enigma was operated by German communications agents working in pairs. One to operate the keyboard entering the message. As a key was pressed, the corresponding letter would light up on the lamp board and be written down by the second. It worked like this. A simple electronic circuit. If you're unfamiliar with this type of thing, think of the wire as a tube that carries electricity. That's close enough for what we're doing today. When the switch is down, the signal flows. When that signal touches a light, it will illuminate. Now imagine that there are more of these simple circuits, 26 of them in all, A to A, B to B, and so on. If the connections between the key and the light are changed, then the signal would be encoded. You press the A key and B lights up. Knowing what letters were connected, you'd be able to decode it as well. That's the job of Enigma's encryption mechanism. It physically swaps the electrical connection between the key and the light. So maybe you've made a code like this before. When one letter is replaced by another like this, it's known as a substitution cipher. But no matter how much the key is scrambled, substitution ciphers are trivial to break. Enigma was more. The heart of the Enigma's encryption engine are several rotors. Each had 26 electrical contacts on each side and could be turned to set the machine at any of those positions. Internally, a wire goes from a contact on one side to a different contact on the other. So the signal might come in to index 0 on the right side and be wired to index 8 on the left, then 2 to 21, 3 to 14, and so on. If it remained as a simple substitution cipher, it would be just as easy to decode. So Enigma accepted 3 rotors, each with different internal connections. And there weren't only 3 rotors, but a set of 5 to choose from. And those 5 could be entered in any order for 60 possible combinations. And when mounted on the internal spindle, the rotor's 26 connection points lined up, and a signal would be sent through them. Coming in from the keyboard, be switched to different indexes by each rotor in turn. Oops. And after 3 rotors came a special symmetric rotor called a reflector. Here, if 1 becomes 10, 10 becomes 1. After passing through the reflector, the signal would be carried back on a different path of connections. This is how Enigma both encrypted and decrypted. Because the path of the signal is symmetrical, typing the cipher character will return the original. But no matter how many times a letter is changed, it's weak if A always becomes E. So the rotors rotated after each character, the signal taking a new path through. The same key pressed twice in a row would yield 2 different encoded letters. Techniques that make a substitution cipher, therefore, easy to break. They rely on repetition, and therefore they're useless now. A key that changes not once a day, not once a message, but every keystroke. And they didn't all rotate at the same speed. The second wheel wouldn't advance until the first one made a full revolution, and so on. Whoops. Back. There we go. That means Enigma is a polyalphabetic cipher with new key every letter based on the starting settings. So each rotor has 26 positions. There are 3 rotors. Makes 17,576 possible starting positions for any given combination of 3 rotors. 60 different possible rotor combinations means 1,054,560 possible settings permutations. But the German military Enigmas had another layer of encryption that commercial versions did not. At the front of each device was a plug board with a connection for each letter. Up to 10 combinations could be made with short jumper cables. Cables that would change the signal's value between the keyboard and the rotor mechanism, effectively making small arbitrary changes to the cipher's key. In order for the German military to be all speaking the same cipher, a chart would be sent out from high command prescribing which settings should be used on a given day. Essential coordination, because only by sharing the same starting settings would agents be able to communicate. The chart included which of the 5 rotors to use and in which order, the starting positions of the rotors, and the 10 pairs of plug board connections. Combining all of these options takes the possible settings to an astronomical 150 million million. Portable electromechanical encryption equivalent to a 67-bit encryption key. Enigma has a practical link to early computing history, and because of the events of its time, we can directly connect Enigma and Bletchley to what we do and why we are here. It's a remarkable object, and that's a key word for today, object, because Enigma will be our platform to explore principles of object-oriented programming, OOP. OOP. A strength of which is said to be how it models the real world. But objects in the real world are very different than objects in a codebase. Enigma, on the other hand, is a physical device. It has moving parts, actual objects that each perform a part of the larger whole by sending messages along a wire to other objects. If the image we're supposed to have of OOP is objects sending messages, well, Enigma might as well be its mascot. We can recreate this mechanism in code without abstracting our conception of an object beyond recognition. Because we could literally hold in our hands the pieces of an encryption algorithm. So let's go big right from the start with two truths of software development. Requirements will change. And this is good. If nothing needs to change, there probably aren't any users, and we need to find another job. And we will never know less than we do right now, because we don't know how things will change. And it's frustrating when we can't make changes, right? When a new feature request comes along and we can't deliver it, or we can't deliver it fast because it's too hard to implement. That's an awful feeling, right? We don't want to be there. But if we don't know anything, and it's all going to change, how do we build anything at all? Object-oriented design is one strategy to do just that. Design is about making change easier by managing dependencies. So, what principles might we explore? Single responsibility principle. We'll gather together the things that change for the same reasons and separate those that change for different reasons. Abstraction. We'll manage the complexity of implementation by substituting a more easy to reason about representation. Excuse me. Encapsulation. An object's internal data should change on that object's own terms. Dependency inversion. Conventional architecture would have utility modules, the low-level ones, consumed by higher-level ones, but will invert this thinking and increase reuse from top to bottom through interfaces. And the open-closed principle. An object should allow its behavior to be extended without modifying its own code. All of this in service of small, simple objects sending messages. Questions so far? Doing good, great. Okay, a little quick poll for me. We're kind of out of the talky bit, and we're gonna be doing more of the workshop-y bit now. So raise your hand if you know or you can define how you would use at least one of these phrases, at least. Cool, so keep your hand up if there are two that you'd know. About three? All five. Now let's switch it up. If you're not familiar or comfortable with any of them, raise your hand. Okay, all right. So everybody, of course, is welcome, but I do think you'll get more out of the workshop if you're on the lower number end of that spectrum, but I hope that we're gonna have some fun together today on Hack Day. And I think Enigma also is a fun, small project to build when you're picking up a new language. Try to build this little toy app in the idioms of the new language that you're learning. I know that's how I use it, and I keep coming back to it. So it's something that at least should be something to take away, even if OO is your complete and total jam already. So how are we going to work? This also is the GitHub repo URL for the repo to clone down. Hotel Wi-Fi has been pretty good so far, but I do have physical copies if we need it. This will mostly just save you some typing. But how are we going to work? Yeah, so everybody should get the repo. If you want to start from an empty folder, that's great. We're not going to go into too much detail about writing the tests specifically, so you might not have those along. But if you want to follow along, any level of participation with the repo, perfectly good. I'm going to code, I'm going to talk a little bit, and you're welcome to use that time how you work the best, listening and watching, following along, typing in your editor, checking out commits from the repo as we go along, whatever's your jam. And at least twice, I will stop up here after going over some concepts, and you'll have time to work out the next steps for yourself. Try your own solution, think about the OO principles that we've gone over, and I'll be around for questions and help and whatnot, and you can take breaks and things like that. Then after that, I'm going to come back up here, show you all how I did it, and we'll sort of loop that until we're out of time. Code and talk, code and no talk. Repeat. So if you've got questions or concerns as we go and you think they might be helpful to someone else in the group, raise them. We're all in this together. The only risk is me losing my train of thought, and I have no doubt that that's going to happen pretty much anyway. So I do reserve the power to rescind that right at any point without explanation, but I think we'll be okay. And I also reserve the power to RAFO any question. RAFO is borrowed from an author I love who borrowed it from another author who I don't know, and it stands for read and find out. It's when a fan asks a question that is so spot on, it's about to be covered in the material anyway. Good? Questions? Great. Essentially, we're just going to mob pair on this little challenge together. So let's start. Now I want to mirror you. Okay, and the display is different, so we're going to do that. Okay, cool. No, don't want to close that. Awesome. So if you've got the repo down, make sure that you can check out initial commit. So we'll get started. Let me fire up my iPad here. How is the font size? Do we need to go bigger? I know the tables are the best place to be. Small. Okay, great. Looking better? Better? Cool. Good. Awesome. Load it. There we go. Cool. Okay, so the initial commit, there's not really much here yet. It's just kind of getting us started. But the one that might be interesting is wiring.rb, because these are the arrays for the rotors that we'll be using. And you'll have to come up with your own on the fly if you don't have that or anything. These are the actual positions for the World War II Army Enigma rotors. So those first 5 are the rotors that would go in the Enigma machines. The ETW rotor is the Eintrittswalze, which is the entrance rotor. And that's basically just the alphabet. And the UKW is the Umkehrwalze, which are the reflectors. And remember, those are special because they have to be symmetrical, going each way, but the other rotors do not. Cool. So as we're talking about these kind of things, a lot of language that we use while we're talking about code modules, we kind of personify code modules a little bit, right? They know things, they talk to each other, they have collaborators. And so if one of those is kind of fuzzy, you don't know really what we're talking about when we say one of those, I would like to stop and kind of unpack that a little bit so that we're all on the same page. So if one of those phrases come up and I don't stop and kind of talk about it a little bit, then we'll unpack it together. Cool. Does anyone who is furiously typing down these arrays want me to keep this up for a second? Cool. All right. Already? I didn't think live coding would fail so fast. Oh, yeah, I didn't have that tag. Cool. Oh, goodness. Cool. So we're going to start with a couple of tests. We're going to use mini-test, which is the Ruby's built-in testing framework. If you're not too familiar with it, all you have to do is require mini-test auto-run at the top of the file and use kind of the mini-test convention and inherit from mini-test test. So first few tests here are kind of starting out as that substitution cipher, right? That A doesn't equal A, and that A and B don't go to the same thing, basically. So we'll run these tests just by Ruby and the name of our file. They failed. We haven't written any code yet. So if they passed, I'd be worried.
Any word about what version of Ruby you expect?
I probably don't do like 1.8. Yeah. Yeah, it should be like there's not anything super complicated or anything going on in here. So, and if you want to challenge yourself with a different Ruby, or you want to use the one that you use at work, like, awesome. Cool. All right, so I'm going to open up Enigma RB. I've got a cipher method here, which is what I'm going to be calling our entry into enciphering here. So we're thinking about how the Enigma machine works. There are some basic parts. There's the keyboard that takes the input and turns it into the electrical signal. We've got the rotors, which are our cipher key, changes the letters. Enigma used 3, so we're going to model that here. Let's see. I think I've got a commit for this, though. Cool, okay. Yeah, so I've got the alphabet here that we can work with. We've got a character coming in, and we're turning it into the index on that alphabet array. That's kind of, I'm thinking about that like the keyboard, right? It's taking the input in, and it's turning it into our electrical signal. We've got a couple of our rotors. This is using those arrays from the wiring.rb. And then we're going to put it back. Using the alphabet again, we're taking that index and we're switching it back to a character so that the person who is reading the lamp board is going to be able to write that down. So I'm using the array method at here, and this is instead of doing something like rotor3 index, right? So these are equivalent, but I just think the kind of at for this example makes it a little more clear as we're going along that you're sending a message, this index, through to that array. Cool. That's also actually equivalent to, I don't know if Drew did anything like this here, but you can do that too if you want, but I think the at is a little cleaner than dot square brackets. Cool. All right, so we have now the 3 parts, the keyboard, the rotors, the lamp board. We're going to run those tests again. And they pass. Okay. Still pretty easy substitution cipher. So we've got some green tests, though. While our tests are green, we're going to refactor. And one of the first things that I want to kind of use and talk about is DRY, D-R-Y. That's don't repeat yourself. Everybody's familiar with this, yeah? So I think a lot of the times the way that it's sort of taught to us and the way that we sort of first interact with that, it means merge any repeated code. But I think we should take a look at the single responsibility principle to help us decide what repeated code should be merged. The single responsibility principle talks about a module being responsible to one and only one actor? Another wording for the single responsibility principle is like we had before, gather things that change for the same reasons. Separate the things that change for different reasons. So this file has 4 of those at method calls, and we could extract a method, right, to take away some of these repeated array method calls. It also might allow us to be like a little more descriptive about what's going on here, right, rather than just like a bare array method. So if we made like translate, and we could, let's see, we're going to need to have our rotor, we're going to have our index, and then we'll return rotor at index. And now, which of these, I may have kind of given it away a little bit calling it rotor, but like, which of these do you think that we're going to collapse? Which of these are going to be the same thing? So it's all just variable assignment or return value that is changing a value based on an index and an array, the alphabet array, the rotor array. It's doing the same sort of thing. But if we change the way that we represent the cipher key, like if it wasn't an array anymore, if it was a hash, would all 4 of these change? They wouldn't, right? The alphabet one would stay the same because we're changing the cipher key, we're not changing the alphabet and the way that that's going to work. So the concept of those purposes are a little bit different. So if we why is rotor 1 not in? Oh, because I took it out of the file. If we're going to do our translate, I always feel like it's the Heisenberg uncertainty principle. Like I can type fine except when people are observing. Right? Okay, we've got translate now. We're using our rotors, and we're passing in our indexes. Let's make sure that our tests still pass. Okay, thank God. So we have kind of collapsed together these things that are going to move in unison, right? We've created a single source of truth here, and that's really what dry is kind of getting at. We want to collapse all of the things so that we have just one place to change it if something's going to need to go and change. If we have 3 ats there like we had before, and we need to update that because we made our hash, and this example is a little contrived for it, but you only change 2 of them, then you've got problems and everything. And if you put all 4 of them in, and you need to change for one reason but not the other, then you've got to extract the abstraction that you've already put together. So you're making extra work for yourself in the future. Cool. Good so far? Yeah, all right. I am hot. So single responsibility also applies at the class level as well as in the kind of code as you're going along. And so what's our Enigma responsible for here? We've got a couple of different things going on. We've got the input translating to an index. We've got the ciphering. And then we've got the index going back into the output. So if any of these changed, like we wanted to OCR an image of a letter and pass it in, then should that go in Enigma? And would like the Enigma class code have to change for that? It would, right? Because this translation is happening right inside the Enigma class. And so we can separate out those responsibilities by making some collaborator classes. Collaborator is one of those kind of words. We're talking about just different code modules that work together is essentially what collaborators are. So let's separate out those responsibilities. Yeah, because OOP is all about architecting for future change by mitigating dependencies. And our dependencies are right here baked into Enigma. Enigma has to change if those dependencies change. So how can we insulate Enigma from having to update? Go to another commit, and we could type it out too if that would be more helpful for everybody. But let's go here. Nope, that is the wrong key. That's the one. Cool. All right, so we've changed this up a little bit. We've still got our translate method that we were using before, but now we're going to extract some of the functionality that we had right in line, and we're going to make some new classes. We've got a keyboard class and a lamp board class, because I'm thinking about our domain, right? We're not doing this in a vacuum. I'm thinking about the Enigma machine. How are we going to model the Enigma machine? It's like, oh, there's a keyboard that does that part, a lamp board that does that part. It gave me some names right off the bat. We are, and I know probably some of you are cringing at this, but we'll get there. We'll get there. We are making an instance variable for that keyboard, for that lamp board, and if we go take a look at either of these classes, they're pretty simple because we had the one thing that was going on for now. We took that out, we put it into its own file. It can have its own tests. If it changes this process, like we need to use a different alphabet or something, that alphabet's no longer baked into the Enigma, it's kind of separated out. We've separated those concerns, we've separated those responsibilities. So this is a step in the right direction. Looks pretty similar, but they are in different directions, right? One is going from letters to numbers, and so you're indexing, and another one is the other way around. So now the changes in either of these conversion processes are able to stay in their own classes and their own files. Oh, okay, cool. We're already at the first mission.
They're required to be the same alphabet, though, right?
I mean, yeah, because unless you knew that the setup was that you were changing it into like an alphabet of emojis to be a further level of encryption, right? But if you had the same alphabet, like you could, right?
The use case is round trip.
Yeah, exactly,
Right?
yeah.
So they have to be the same.
Right. Yeah, it's hard to Morse code Unicode for emojis anyway, so. Cool, okay, so if you check out the commit that is called first-mission, and look at the Enigma tests. So we've got some new tests in here. So we are going to add the repeated character changing into a different character. Because right now, as it is built, you send in A, it'll send back whatever. But then if you send in A again, it'll give you the same letter all over again. And so we need to add a mechanism that will advance those rotors, right? Because we're thinking of those rotors turning. You don't need to get super complicated into the full rotation advances the next one unless you're fully ready to go after that. Then by all means do. So the job right now is we'll give you a few minutes and make this test pass. Think about how we extracted some classes before. Likely, this is something that you've done plenty of times, and yeah. Cool, I'm gonna turn this off for a sec and give you a few minutes. I wrote down 20, but I don't know that we'll end up using all that. We'll see.
Is there a commit we're supposed to be starting from?
Well, there was initial dash commit, had the empty files, and then this one with these tests is first dash mission. So I'll write that up here. Good call out. All right there. That'll give you those 3 tests. No, Copilot, go away. That'll give you these 3 tests here and that commented out one at the bottom. If you want to make it encipher a phrase, if you've done the first little part and you want to go forward with that, then you can uncomment that and move along. Sweet.
Sorry, is first mission the name of the commit?
Yeah, there's a tag. So, yeah, git checkout first dash mission.
Are the tests supposed to be tagged in?
This third one will not. Yeah. Yeah. No problem. Not only can you keep Enigma in your head, it can still pretty much all fit on the screen here, too. How are we doing? Feeling like I can talk a little bit more as we're wrapping up, if you're still going. So, we've got our test that expects that we're going to have a behavior of an advancing rotor, so that two repeated letters are not the same ciphertext. So, the kind of thought that we're putting into play here is I think we're really leaning into encapsulation and abstraction, because take a look back here at our Enigma, where we extracted our keyboard and our lamp board. So before we made the keyboard and the lamp board, Enigma had the alphabet in it. It also used the @ message, and what that means is that our Enigma class depended on those rotors being arrays, right? So the @ method would have had to change, like we talked about if we were using hash or something different. So that's kind of what I mean when I say that Enigma knows about something being an array, right? There's something in Enigma that is assuming one of its collaborators is a certain way, has a certain method, is doing a certain thing. And the way that we can kind of separate out and allow for a little more freedom, a little easier changes, is to, instead of relying on specific things like that would require a certain thing, is to kind of put a layer in between, right? And abstracting it away. That's what we're talking about when we're abstracting. So something like making a new class that would have a method, and you'd call that that method instead of just assuming it's an array, because then whatever class you have, as long as it has that method, Enigma knows how to work with it, right? We're duck typing, we're doing all of our fantastic Ruby things. And so, with the keyboard and the lamp board pulled out, Enigma doesn't know about the alphabet. You can make it whatever alphabet that you want. Yeah, oh, abstraction, I wrote that. I guess I talked about that, great. So, we've made Enigma into a simpler object. It's sending messages to its collaborators. Rather than telling its collaborator what to do, it's saying, hey, keyboard, I need you to convert this. Rather than, keyboard, you convert this by doing X, Y, and Z. So let's take a look at how I went to do this. So we know that we want to extract a rotor class, right? I've got some tests here that are in the next commit if you want to get them as well. But okay. So now what we've got is, I'm writing the test first, and I'm kind of thinking about how I want the interface, how I want to be using the rotor and what that's going to look like once I've written it. So we're going to have a rotor, and we're going to be able to pass in the key, right? So we can use this class for any of the different rotors. So we'll have that as an argument. And knowing that if we are going to send in 0 based on this key that we have right now, I'm going to expect 1 back, and so on and so forth. All right, okay. Check out rotor position. Good notes, me. Except maybe not. Great. All right. Don't know that this will be as readable, but let's see. Not great. Cool, so let's take a look first just at the kind of initial initial pass at a rotor class. So we're just extracting it, right? We're not moving on to the advancing part of the logic yet. We just want to set up this relationship between the rotor and the Enigma classes. And so I'm just taking what the rotors were doing in Enigma already and making that in another class, in a collaborator like this. So we're passing in the wiring, which would be the same as that we were just using that array directly. We're going to pass in that array like we saw in our tests. And then we're calling .at. So it's the same exact thing that we were doing in Enigma, but we're removing the specificity from Enigma and putting the specificity into the rotor class. And how does that change our Enigma? Again, we'll get to this. So in much the same way that we did with the keyboard and the lamp board, because this is kind of the skill, this is the thinking that we had just used, we're going to use the same, apply the same steps, the same logic. We're going to have rotor 1, 2, and 3. They're going to be instances of our new class, and we're setting them up like we had before with rotors 1, 2, and 3. Come on in. The water's fine. And like we were doing before, we're just kind of moving that same operation, that at, we moved it into the rotor class. We saw that already, and that at is now behind the translate method on the rotor now instead of in the Enigma class. So we actually get to remove, remember that translate method that was inside Enigma, because translate is happening inside our rotors now. And so we can just, instead of calling that within the Enigma, we are sending a message to one of our collaborators to call its translate method. But it's still operating the same way, right? We're not advancing, we're not keeping track of the position of the rotors or anything like that. So our test, that's it. Is still failing. Right, so this is that failing test that we were working to get passing. So we need to teach the rotor about how to think about its position. And so we'll go into rotor. And we are going to make this an instance variable. Let's see, we want position, and we'll start it out at 0. So when you make a new rotor, it's just starting right out at that first index. So we are making the rotor the only thing that knows about that position change right now, and the rotor is going to handle all of that itself. But we're going to have to end up using that position right now because we've got this wiring at, it's not regarding, we're not doing anything with that position. So I'm going to make a method called step adjusted key. And we'll have our key rotate. Thanks, Mats. We're going to rotate the number of positions that we've got. So .rotate instead of .rotate bang, it's not modifying our array. It's going to give us back a new array with the indexes shifted over a certain number, and that's exactly what we need to do. It's even called the thing that the rotor is doing in Enigma, so that's nice. The key, yeah, right. Okay, cool. I called it wiring over here and key over there. Thank you. Pair program. Cool. All right, so we're rotating, but this position is still not changing, right? We're not having the accessor, we're not letting Enigma reach into the rotor class and change that position because it would be the same thing as before, right? It's specifically telling the rotor how to do its job. So we want to keep that away from Enigma. So we're going to have to update how this translate works. Well, first of all, we are going to want to use the step adjusted key instead of the just the straight wiring that we've set up. Let's call it, actually, let's just make that the same all around. Yeah, so now it's going to be using that position, but there's still nothing that is moving the position of this rotor. And so we'll have it advance. But now we want to make sure that we return this. So let's do ciphertext equals, and then so we can bring our ciphertext back out. And this is modeling the way that the Enigma worked. It would advance after the key press. So really, you could have that go any way that you want. If you don't like that intermediate variable, yeah, sure, advance first. We're going to need that advance method now, though. Nope. Just add one. And just move it along, one tick. And we need to control for the end of the thing, so if it falls off of the end, typing so deliberately. Great. So if we've fallen off the end of our key, we'll jump back and start over from the beginning. Especially for that first rotor that's turning after every press, that's probably going to happen quite often. So we want to make sure that we're controlling for that. Okay, we're advancing. We are keeping track of our position. We are using that position to modify our key as we translate. So I'm expecting that those tests are going to pass. Ding, ding, ding. Nice. I know there were some issues and stuff getting started for some folks. How many people got that test to pass? Is that going along? Nice. Cool. Awesome. Good. All right. So with all of this here, we've added this advancing. We've added this position. We have updated that so that our test is showing us that we're operating a little bit more like the real Enigma machine. We are setting up that 17,576 different positions instead of just 26, so we're on the way. Well, actually, right now it's still just 26, but we'll get there. And we did all of that without Enigma having to change beyond extracting the rotor class, right? So we've changed the behavior. We've extended the behavior of our rotor class, but nothing here in Enigma had to be modified. And so if you can think about this in all of the different ways that your requirements might change, one module might sort of change and need to do the at a different way because of new business rules or whatever's going on. If they're encapsulated and they're separated through abstractions properly, it's going to be an easy change that's not going to spread across multiple files, have to update tests everywhere, that sort of thing. And so this is one of the ways that these OO principles are protecting ourselves for the future, making change easier through managing dependencies. Yeah, and another thing that, another kind of term and way that we talk about the interaction between collaborators in an OO way is we talk about coupling, right? And so coupling is a term that means that two modules they don't have their own responsibilities, right? They work really closely together, and a change in one is going to require a change in the other. So where we had the Enigma directly accessing array methods, that would be tightly coupled to that array class, but now here we're loosely coupled with our rotors. I like to personify my code modules, so we've got our small simple objects sending messages, and it's the way we talked about it before. Enigma is asking a rotor, hey, can you translate this? So if you think about that, I play board games with my friends. I would say like, hey, can you bring over that board game we played? Instead of, hey, can you go over to your living room, pull out that game we played from the third shelf, go outside and put it in your car before you come over? I don't care how they got that game over here, right? That's their responsibility, and it's that same sort of thing that we're creating with these two classes. All right, so the next thing that we're going to do, we're advancing, and we want to encipher a whole phrase. We want to be able to pass in a long string so that we are not just doing it one at a time, right? The Enigma machine had to do it that way. We're in code. It can be a little bit easier for us. So we're going to modify this cipher method here a little bit. We're going to separate out all of the characters. Again, we have a nice little method that'll do that for us. We've got multiple enciphered characters. Over the message characters, we will .map. This is all kind of the same thing that we want to do. Move that over. Great. Oops. Nope, still did the same thing. That's fine. All right, so that's fairly easy change, or fairly not very complex change to make. We're just doing the same thing that we were already doing for one letter. It was working for us, so we're going to do it over every single letter that we're passing in our message. Let's take a look at that Enigma test file and comment it. And I think I've got the right setup here, but I might not. I've got a... Oh, yeah, okay, all right. I on the fly, thought I could adapt for the small screen size, but I ruined it anyway. Thank you. Nice. That might just be because no, let's see. Yeah, I can't remember where I changed that in here. But so we are enciphering a phrase. We're not like erroring out or anything like that. But we are operating a little bit differently than the actual Enigma did, because every single one of our translate calls is advancing our rotor once. And so every single one is still moving in lockstep. We're changing the key every letter, but there's only 26 of them now instead of our 17,000 possibility, right? That's where my notes end. So like we're just going for it.
So is it expected that the rotors would have independent state?
Right.
Or is the offset always identical for each rotor?
It would not be. Like currently it is, right? Because they're all moving, they're all getting the advance command, and so those positions they're independent, but they're all moving kind of in lockstep. Yeah. And what we need to do is to have one rotor go a full revolution and then send a message up to the second rotor. I've gone a full revolution. We need to move one forward. Step and advance that one. So let me just discard these for now. Oh no, discard. Oh. That was terrifying. Adds position, enciphers a phrase. I think this is... Okay. So we've updated a little bit here because, like we were saying, our rotors are kind of communicating across each other now. So they can't just manage their own state because they need to be sent a message from the rotor in front of it. Have you moved to full revolution? Okay, great, then I need to. Have you moved to full revolution? No, then I'm going to stay put. So that needs to move up into kind of a scope above, right? Where is the place that can see all three of those rotors? That's in our Enigma. Our Enigma is the orchestrator right now, right? So it can see all of our rotors, and it's going to handle the advancing. So what I've got here is we've still got our message. We have the map, same as it is. And what am I doing here? Yeah, and cipher index. So we've extracted, because this is starting to get a little complex, I've extracted a method here in cipher index. And if we go down here, this looks like what we had before. We're shifting the index, translating it through a rotor, shifting the index, translating it through the rotor, same as before. Then we come along, we're going to advance the rotors because Enigma is taking on this responsibility. should not. Taking on this responsibility, and so we've got this advance rotors method here too. So if rotor 1 advance, if rotor 2 advance, rotor 3 advance. So there's obviously something more going on with advance than we had before, right? So we've moved this responsibility up a level into Enigma, and let's take a look at how we've changed rotor to do it. So the same as before, position is our instance variable inside rotor. It's still not something that we are allowing someone to edit directly, right? We didn't see that Enigma is saying rotor position plus equals 1. We're still doing that inside the rotor. We've still encapsulated the responsibility for directly changing that variable within the rotor instances. This all looks the same here with the translate, but we've moved the advance, we've modified the advance a little bit, that we're going to be sending back the message true or false if it has completed a full rotation. So now advance is being called from the outside, and it's getting some feedback from the rotor. The rotor is sending up, have I completed a full revolution, essentially. The rest remains the same. So step adjusted key is working on translate in just the same way. So if we take this advance method and we go back to where it's called in the Enigma, we can see how this if statement is working. So if the rotor 1 advance has gone a full revolution, it's going to return true, and we'll advance rotor 2. And if rotor 2 has gone a full revolution itself, we'll go and advance rotor 3. Isn't it good? Follow along? Great. So let's see if I set these tests up right or not. No, because there's a typo. I remember this one. One of these commits has a typo that's supposed to be a V, but I typed G. So let's fix that. So watch out for that. Okay, great. So it basically went manually into hello world and went through all my rotors to make sure that it was coming out in the phrase that I expected. And here we go. We're asserting on the actual, like manually checked, although who am I, that those strings are what we're going to expect if it's operating the way that I want it to be, correctly advancing the way that we just set up. Okay, but what's changed in our Enigma? Some of this responsibility has bled back up into Enigma, right? Like it was so nice before when the rotor was doing all of its stuff itself, and Enigma didn't need to know about any of that, right? We could change rotor, we modified it, we did the advancing, and Enigma didn't have to change its calls to translate at all, but now they're coupled again, right? So they're a little tighter, more tightly coupled than they were a moment ago. And that's not necessarily a bad thing, right? Coupling is going to happen. Coupling is what makes a system work, right? If your code modules are not talking to each other, they're probably not doing very much, or they're doing everything right in there and you're just working in one file and yikes. Yeah, so what can we do to get our Enigma back to that kind of clean place where we were, where a change in one of these subsystems, right, the enciphering kind of subsystem, what can we do to encapsulate or abstract that away from Enigma? Well, what did we do to encapsulate and extract away the lamp board, the keyboard? We made a new collaborator because our Enigma has picked up another responsibility. Right? We had before that it was turning letters into indexes, then it was doing all of the translate stuff, and then it was turning that index back into a letter. And we were able to kind of separate out those concerns so that the Enigma was just orchestrating. It was just kind of moving things along. But now it's moving things along and being the one to advance our rotors, right? So as I'm thinking about how I want to model this and how I want to extract this and get back to that state that we had a little while ago, I'm thinking about the actual Enigma machine. So we've got our keyboard, it's going in through the rotors, it's coming out through the lamp board, but there's another part of the mechanism there, right? There's a spindle that those rotors are sitting on, and it's doing the little kind of advancing and moving the rotors along. Because if you think about it, the rotors have their own positioning and everything like that, but there's another mechanism that's pushing them along. They don't have a little internal motor moving them along. So I'm starting to think we've got the orchestration in Enigma, and we've got the advancing and kind of the orchestration between the rotors. So let's take one of those responsibilities and make it its own class, make it its own object. Let's see, do I have a, yeah, cool. Let's go take a look at my commits. I hope this is the one. Yeah, cool. Okay. So we've got something that looks pretty different now. We've removed the rotors from the Enigma completely. And this gives us a lot of stuff that we might not have thought about at first. Before, Enigma was locked into 3 rotors. You had to give it 3 rotors. That's all it would work with. Now, because we're in code, we don't have to build a bigger physical device. We can put in 9 rotors. We can put in 13, whatever. Enigma doesn't care. It is just sending a message to its collaborator, the spindle. Could you transform this? Can you do the cipher for me? Just the same way as asking our friend to do the board game. It doesn't care how it's doing that. We've separated those concerns. So let's take a look through our ciphered method. Doing the same map, just like we were before. Keyboard is still converting. We're asking our spindle to transform. There's only one call to it. We're converting back, and we're joining. So our Enigma class has gotten a lot simpler by removing that complexity out. We've abstracted it. We were talking about before in the slides that abstraction was removing complexity to have an easier to reason about process or thing in its place. That's the spindle now. Let's take a look at our spindle. And our spindle is going to look really similar to what we were doing in Enigma, just the same way that our keyboard, our lamp board looked really similar to what we were doing in those steps in the Enigma class. We're just starting out by pulling it into a new place. We're abstracting that away, but the behavior doesn't have to change very much. So our spindle, currently we're still initializing it with 3 rotors. We are doing the transform, the translating, just the same as we were. Then we're advancing, we're using that true false. So to do this abstraction, nothing in the rotor changed. We simplified the Enigma, and we put that complexity into the spindle class. Another thing that I love is that you can write tests about this one specific thing. This one part of the process gets a little more test coverage, gets a little more reliable in that way that adding more specific tests can, without having to test internals, right? You're not testing the how of Enigma, but you're testing the inputs and the outputs of Spindle. Do I have Spindle test on here? No, of course not. That'd be great, so I didn't. Awesome. Cool, let's make sure that those tests still pass. Okay, good. Awesome. Let's double check that's because I fixed the typo in this commit too. Yeah, it is. Great. Cool. Questions? We're seeing what we're doing. We're kind of picking up the methodologies that we're starting to work with here. Awesome. Cool. Now there's something in here that I've been kind of alluding to as we've been moving along. That I was saying that there's something that might be giving some of our more experienced programmers like a little cringe, because there's still a lot of coupling going on here. We've extracted out these responsibilities, but there's coupling between the Enigma and specific classes of its collaborators. It's collaborating with a keyboard, a lamp board, and a spindle, but it's only ever collaborating with a keyboard, a lamp board, and a spindle, right? It is depending on those three classes specifically. So what can we do to abstract and kind of tease those apart? We're going to use dependency injection. Let's actually, we're going to, what did I call this? Transformer. Okay, so we're going to pass in some keyword arguments, and this is going to look a little bit different. Just for now, we can keep those keyboard lampword. And now, here's another way that we know that it's gotten a little simpler. Ding. Actually, do we even need the wiring? We don't even need the wiring in here, do we? Oh, look at that. So instead of having those classes directly in Enigma and coupling those together, we've separated that out. We've made change easier for ourselves once again, because now instead of having to go in and change the keyboard if something needs to update, we can give it a different kind of keyboard, right? The Enigma on the inside doesn't know about specifically how something is being done, so you can change how that thing is being done at your will. If you might say that the keyboard is going to change, well, we're going to go change the keyboard, but what if you still need that keyboard for some of your users, and a different set of the users need a different keyboard? Say, some need Cyrillic, and some need kanji. Different, I don't know how the Japanese enciphering device is completely different, but yeah, you can change that up to your heart's content. So let's take a look at what that makes our, but that does, the way that we're using the Enigma is going to have to change for that, right? Everything isn't baked into it. I cannot tell where anything is. Cool. Yeah, all right, I did note so. So we're looking at the tests here for Enigma. And instead of just enigma.new, since that initialize has those keyword arguments, we're passing in, we're using dependency injection, we're telling Enigma about its dependencies when it's being initialized. The way that Enigma is going to be used is different. There are a lot of things that you can do to not have this. If you think that this makes your .new look messy, maybe there's a lot of complexity going on in there. You can have defaults in your Enigma, things like that, but kind of for just straightforwardness and fitting it all on the screen, we're going this way here. So we're testing basically the same thing, but we're initializing our rotors. We are passing that test rotor into Spindle, because now Spindle, if we'll take a look at that, is doing the same dependency injection that we're doing in Enigma. We're decoupling these classes as we go along. Yeah, I think that is the majority of what's going on there. Looking good. Let's take a look at Spindle too. Yeah, okay, so Spindle is looking a little bit different here as well. So we are passing in rotors. Like I said, we wanted to get to that place where you can have 3 rotors, you can have 5 rotors, you can have 9 rotors, anything like that. And so we're passing them in as an array. We've got an array of rotors here. This is just so that you can have them as arguments. They'll get splatted into that array. And so now our transform is going to look a little bit different. We get to use one of my favorite methods, but one that a lot of people are not really fans of. I think if you use it a little bit more, it comes easier to reason about, but we're reducing. So we're taking that array of rotors, and we're iterating that over, and we're kind of passing information along between each iteration. So we can do translate, which is giving us our true false. Oh wait, no, sorry, that's the advanced step. So we're still doing the transformed index, but we're doing it in a way that doesn't care about the number of them. We're not setting a variable and translating over specifics. Again, we've extracted the specifics away. We're reducing over them. We're doing the same sort of idea with our advanced step. And reduce here, we are saying if there is a true that comes back from that rotor advance, then we're going to pass that along to the next one to know that it should advance as well. what's going on here with the reduce has an argument. The argument here of true is because we want that first rotor always to advance. And so if a rotor needs to have a true from something to tell it to advance, if the spindle tells the first rotor every single time true, then that first rotor is going to advance, and it'll pass its true falses up the rest of the chain through this reduce. Good? Sound nice? Let's take a look. What do we got here? We are got a spindle. Spindle's not depending on. Cool. And we're taking a look. The same way that the way that we used Enigma changed, the way that we're using the spindle is changing too. Here we've only got 2 rotors. They're a lot simpler than rotor 1, rotor 2, rotor 3, the actual Enigma rotors, so that we can kind of reason about it a little bit better during our tests. And we're even mocking out a rotor to make sure that we're sending the true false from the advance the way that we want, so we can test on that as well. So let me see. Okay. So the sort of last, or not really last, but the last crucial part of how an Enigma operates is you need to be able to send the same the cipher phrase into it and get the original message back out, right? And so that is going to require our reflector rotor. And that's, if you check out second mission, we should have the tests that we need to do that. Right, here we go. This is, it's updated the tests to work with the way that we've changed the spindle and injected that into the Enigmas and everything. So they're getting a little bit more complicated as the way that we use the Enigma gets more complicated, but the code modules have simplified. So we've got this test now of a starting phrase, versatility. This is, and I don't know if my pronunciation is good or bad, so we'll just say it's good and move on. This was one of the phrases that showed up a lot in messages because German control would send out a weather report, Wetterbericht, to the field agents as they were going along. And so there were some messages, they were like, let's try this phrase. Can we find this phrase? And that's one of the ways that they would kind of have a hook into encrypting it. So we're using that same phrase here. We are starting with Wetterbericht. We're ciphering it. We're initializing a new Enigma with the same settings because the Enigma we used to encipher it has advanced its rotors a bit. We're making a new one starting at the same starting position. And we are going to see if our deciphered phrase turns back into the starting phrase. All right, so we'll have probably a little bit more time with this one. This one's a little more complicated than before, but take a crack at it. You see here, one little hint is, like I was saying before, you could change the keyboard and still keep the old keyboard around. You don't necessarily need to make a new, or change that spindle how it works. You can have a reflector spindle that will do that back and forth. Yeah. Yeah, that was a great question. Does the advance happen at the reflector? Like, where does the advance happen? So the advancing of the rotors, that step, is going to happen after the lamp board has lit up. So like the full process through from key press to lamp board, then we'll advance the rotors once. Yeah, so we've got a lot of questions about how the reflector rotor works to make this symmetrical. And so I'm going to try and find that slide. So in the wiring.rb, the reflector rotors are the UKW rotors. And whereas rotors 1, 2, 3, 4, 5 are essentially randomized, you could throw in really whatever indexes you want in there. I just used the ones from the World War II rotors because I thought it was cool. What are you doing? But the reflector rotor is specific in the way that those numbers are laid out. So if you send in a 1, it'll become a 7, just throwing numbers out there. But if you send in 7, it'll become a 1. So they're matched pairs. Whereas in the other rotors, if you sent in a 7, it could become a 9. But if you sent in a 9, it could be a 22. Right? They're not pointing to each other the way that the reflector rotor does. See how the wiring in that last one, the reflector rotor, they match each other. There's kind of only one side to the rotor, if you want to think about it that way too. And I probably should have made this so that they didn't cross, so it would be a little easier to understand at first glance. But you see the way that if you took the path, instead of going from A to E, if you sent in E, it would follow the same path and end up back at A. And that's how the encryption-decryption with the same setup works. So it'll go rotor 1, 2, 3 through the reflector, rotor 3, 2, 1. And you'll have your result. Is there more questions that are kind of coming to your mind as you're trying to grok this? Because I know this can be a little twisty. In the Enigma setup, like the actual machine, there's only one reflector rotor. And that one doesn't rotate either. Yes, there were multiple reflector rotors that you could set, and especially like the Army, Navy had different ones altogether. So again, just more wiring possibilities. But that one would just kind of sit stationary and make sure that it was symmetrical. You're doing in 2 hours what it took me months to do for this talk, so you're doing great. Yeah. So the question is the reflector the special sauce that makes it able to use the same settings to decrypt and encrypt, right? So the way it would work is every Enigma would know that today we are set to rotors 1, 2, and 3 at positions 4, 5, and 6 with this reflector. And so you could encode a message, so you've got your ciphertext, and then someone else would have an Enigma set that theirs up to 1, 2, 3, 4, 5, 6 in the same way, and because of that reflector, that's the special rotor that makes it symmetrical. Right? And when I mean symmetrical is the A will turn into E and E will turn into A in that particular click. Yeah, exactly. So if you'd receive your Morse code operator would get your garbled up ciphertext, and you would just type those into your Enigma to decrypt and have the message. So it was remarkably simple and just a fantastic idea. The fatal flaw was also the reflector, though, because a letter could never become itself. Because if it's has to be symmetrical and has to go both ways, the wire can't converge. So that mathematically eliminated a whole tree of possibilities, and the mathematicians at Bletchley were able to utilize that, and then Turing built a machine that essentially brute forced it. And so that was the thing that makes the encryption-decryption happen, but it was also the thing that made it weak. Yes, correct. So the number of transits through rotors in this format of 3 rotors and a reflector is 7, because it'll go 1, 2, 3, reflector, 3, 2, 1. So each key press is touching 7 times rotors. Rotors 7 times. Different rotors, yeah. Words. and probably like a lot of problems that we do at work, when you see the solution, you'll slap your forehead and say, that's so easy, but it's not easy to get there. So. Yeah, that's a great thought came up that the test will only pass if you use the UKWA reflector. So it is tightly coupled to that. Okay, we've only got a few minutes left, so I'm going to kind of show you what I did. And there's still so much more that you can do with this Enigma. So if you don't have a Hack Day project, try building that plug board. Remember, that will, before it even gets to the rotors, you can switch individual letter pairs. But let's take a look at, well, I got to get to the right commit. Cool. All right, so we've got the reflector spindle that we see right here. Let's take a look at what is different about the reflector spindle than the spindle on its own. So passing in the rotors, that's the same. We could inherit some of this stuff if we wanted to instead of duplicating this code. But here in our transform, we are going through the rotors, we're reflecting, and then we're reversing through the rotors. The only other part of this that's a little tricksy is you see on line 16 we have translate, and on line 22 we have edelsnart, which is a backwards translate. Because if you think about if going from, what is this, right to left is at on an array, going from left to right is what index is this at, instead of what value is at this index, right? So going through the reverse way is the reverse operation on those rotor arrays. So if we look at the rotor, we've got edelsnart. The difference is just at versus index. I would not, just so you know, I would not name that edelsnart at work. Absolutely. Yeah, it's just down here. So yeah, this is again like we were passing in specifically a keyboard or specifically rotor 1, 2, 3. We've got it tightly coupled to this specific rotor in here. To use a different reflector rotor, the way that this is, the reflector spindle class would have to change. And so my first tool that I would reach for would be dependency injection like the other ones. And this is where inheritance on initialize wouldn't work anymore because you'd have to also pass in your reflector. Yeah, let's take a look at. So we're looking at, whoops, this one right here. So if you look, so say we pass in 0, we see the value at index 0 is 4. Then if we pass in 4 at index 4, it's 0. So the way the reflector rotors are different is that they will always be paired. The index and the value are paired. No, I mean it could be, as right? Yeah, like it could be as long as they are paired. Right. No, that's like a simplified, blown out way so that you could see it. Because if it's a tangle of wires, it would be harder to see. But yeah. Understood. That's good feedback. Yeah, that's how those the UKW rotors are different. Is that the index and the value always go back to each other. Yeah, and so we're down to about just a couple of minutes left. So I'll kind of leave you with that. I would love to, extend this with anybody. If you want to try building out the plug board and stuff, that'd be a fun project to do. I've always wanted to just kind of go crazy with this and see what you want to add elliptic curve cryptography to the transformers. Great, let's do it. So there's so much that you can do now that you have all of these things loosely coupled and working between an interface rather than knowing about the internals of each of these different steps. You can make those steps whatever you want. And yeah, I would love to see if you do something that just seemed like fun and you wonder if you can do it and you made it work. I would love to see it. So thank you everybody for being guinea pigs at my first ever workshop. I think this Enigma thing is really super cool, so I would love if you want to talk about it more or talk about Bletchley or anything at all. Have a great rest of your hack day.